Welcome back to The Deep Dive, the show where we cut through the noise and get straight to the cutting edge. We all grapple with just a flood of information, right? Especially in these fast-moving fields like AI, computer vision.
Absolutely. The need to get up to speed quickly is, well, it's constant.
And today we're tackling one of those really fascinating challenges. How do you take, say, just a handful of video clips and truly reconstruct dynamic moving objects in full 3D? Not just, from one angle or at one specific moment.
Right, but from any perspective.
And at any moment in time. That's the key bit.
It's really about building a kind of digital twin of reality, but one that truly captures motion. Imagine being able to re-experience an event almost like you were walking through it.
Yeah, totally free to choose your perspective, maybe even rewind or fast forward the action.
Exactly.
So today, our deep dive takes us right into a pretty groundbreaking research paper. It's titled 4D-LRM, Large Space-Time Reconstruction Model from and to any view at any time.
Quite a title.
It is. And our mission today is basically to unpack how this new model, 4D-LRM, gives us a shortcut to understanding a really challenging computer vision problem. Reconstructing these dynamic objects and scenes.
We'll dig into its novel approach, how it improves on what came before.
Right, and what it could mean for things like 4D content creation, maybe even real-world applications down the line.
Think of it like getting a clear, almost academic grasp of this cutting-edge paper, but hopefully without getting totally bogged down in the super dense jargon.
Yeah, we're aiming for that aha moment, giving you the core insights without you needing to wade through every single page of the original research.
Sounds good.
Okay, so let's start at the beginning. The fundamental problem 4D-LRM is trying to solve.
Right.
It's about reconstructing dynamic objects, dynamic scenes from video.
Which means building that complete 4D representation. You need the spatial structure.
That's our 3D.
Right, the 3D part. And crucially, the temporal dynamics.
The fourth dimension, time.
Exactly. And often you have to do this from pretty limited visual inputs. Maybe just a few camera angles, maybe gaps in time.
And, this isn't just some abstract academic puzzle.
Well, not at all. The implications are huge.
Yeah.
Accurate 4D representation could seriously change fields like 4D asset generation.
Yeah, for games, movies, AR, VR.
Exactly. Think about truly immersive experiences. And it's also foundational for world modeling in AI and robotics.
How so?
Well, allowing machines to understand and interact with dynamic environments in a much more sophisticated way. If a robot understands how things move and change over time.
It can act more intelligently. It makes sense.
Precisely.
So before 4D-LRM appeared, what were people doing? You mentioned existing methods fell into maybe 3 main camps.
Yeah, roughly 3 categories, and each had its own hurdles. First, you had the optimization-based methods.
Okay.
These would reconstruct a scene by optimizing like per scene or per object, usually from multi-view videos.
So lots of video needed.
Yes, that was the catch. They could produce high-quality results, but they really demanded dense spatial and temporal input. Lots of views, lots of frames.
So if your videos were sparse or incomplete?
They really struggled. Not very practical sometimes.
Okay, category 1. What was next?
Then you had geometry-based methods. These focused more on estimating the dynamic geometry itself, like depth maps or camera poses, directly from the videos.
So figuring out the shape and position frame by frame?
Kind of. They were good at that per-frame geometry, but they weren't really designed for synthesizing novel views or times.
So you couldn't easily, look at it from a new angle or see what happened between frames?
Exactly. They didn't really let you explore the 4D space freely.
Got it. And the third category?
The third was generation-based methods. These used visual generative models, especially things like video diffusion models, to produce what looked like plausible 4D assets.
Plausible being the key word there.
Well, yeah, they had the advantage of needing fewer inputs, which is good.
Yeah.
But they were often computationally really expensive, very sensitive to the specific text prompts you gave them. And frequently, they were tailored for single-view monocular videos, just one camera input.
And that causes problems, right?
Big problems.
Yeah.
It leads to inherent motion ambiguity. The models often prioritize just making it look good, the perceptual quality, over getting an accurate, faithful 4D reconstruction.
Right, like you said, it's hard to tell if something's moving away or just shrinking if you only see it from one angle.
Exactly. The core issue with single-view video is that it's fundamentally ill-posed for true reconstruction. It's just ambiguous.
So that's where these large reconstruction models, LRMs, started showing promise.
Yes, exactly. LRMs offer this sort of rendering-based alternative. They learn from huge data sets to do efficient, high-quality 3D reconstruction.
But mainly for static things.
Primarily, yes. Existing LRMs were mostly for static 3D objects, extending them to general 4D reconstruction, especially when dealing with sparse views from different cameras and maybe missing timestamps. That was proving incredibly challenging.
Okay, so if the old methods were like specialized tools, maybe a bit limited, what was the big question, the sort of holy grail that 4D-LRM set out to answer?
The central question they really tackled was, can we scale up 4D pre-training?
Okay.
Can we learn a generic space-time representation that lets us reconstruct an object from just a few views, maybe at scattered time points, and then view it from any angle at any time?
And the paper's answer
is basically a big yes. It introduces 4D-LRM, which is a transformer-based model designed specifically for dynamic object reconstruction. And it's trained in a truly data-driven way.
Right.
It adopts this unified treatment of space and time. That's the core idea. It represents a dynamic object as a cloud of what they call anisotropic 4D Gaussians.
Okay, anisotropic 4D Gaussians. Let's unpack that. That unified treatment sounds like the real breakthrough.
It really is.
It's moving beyond just thinking of a 3D object moving through time.
Right.
To considering time as an inherent dimension of the object's representation itself.
Precisely.
Yeah.
It's a pretty fundamental shift in how we conceptualize and model dynamic stuff.
Okay, so with that foundation laid, the big question is, how does 4D-LRM actually use this idea to build a dynamic object from, messy video inputs?
Right.
That's where its transformer core comes in, starting with this concept you mentioned, 4D Gaussian splatting, or 4D-GS.
Exactly. And maybe some listeners are familiar with 3D Gaussian splatting, 3D-GS. It's been a big deal recently for static 3D scenes.
Yeah, explain that quickly.
Okay, so 3D-GS represents a scene as a cloud of these anisotropic 3D Gaussians. You can think of each Gaussian as like a tiny, squishy colored sphere or maybe an ellipsoid.
Okay.
Each one has parameters defining its 3D position, its center, its shape and size, covariance, its rotation, its color, and its opacity, like how see-through it is.
So millions of tiny, fuzzy, colored blobs that blend together to make the scene.
That's a good way to put it. They blend together based on those parameters.
So how do you get to 4D?
Well, the genius of 4D Gaussian splatting, 4D-GS, is realizing that space and time are not independent when things are moving.
Right.
This isn't just a clever modeling trick. It fundamentally changes things. It treats time not as some separate track, but as an inherent property of the object baked into the Gaussians.
Okay.
So 4D-GS extends 3D-GS using this unified treatment. This means the mean or center of a 4D Gaussian now includes a temporal component instead of just XYZ position.
It's XYZT.
Exactly, a 4D space-time center.
And the shape part, the covariance.
That becomes a 4D ellipsoid, so it allows for anisotropic deformation, squishing, and stretching, not just in space, but also in time.
Whoa. Okay, so if 3D-GS used these fuzzy marbles, 4D-GS marbles can also stretch and shrink through time. It's like they have their own little internal timeline.
That's a really neat analogy. Yeah, they have temporal extent and deformation. This unified approach means each 4D Gaussian uses, I think, is 20 parameters in total to capture not just spatial stuff, but also its motion and its influence over time.
20 values per tiny blob. Wow.
And this 4D representation gives you a really powerful capability. You can effectively slice through time.
How does that work?
At any given time you want to render, you can derive a conditional 3D Gaussian from the 4D Gaussian. It's like taking a snapshot of the dynamic object at that specific instant.
Creating a 3D view for that moment.
Exactly. And that's absolutely crucial for rendering. It lets the model generate any frame at any time you ask for.
Okay, so we've got these incredible 4D Gaussians as the building blocks. How does 4D-LRM actually create them from the input video? That's the transformer part, right? The image to 4D-GS decoder.
Yes, exactly. So the model takes a batch of input images, could be from arbitrary views and arbitrary times.
So messy, real-world kind of input.
Potentially, yeah. It also needs the camera parameters, intrinsics, extrinsics, and something called plucker ray coordinates for pose conditioning.
Plucker, okay, what are those roughly?
Think of them like a very precise way to represent the light rays hitting each pixel. It tells the model exactly where in 3D space each pixel's view is coming from. It's critical for accurate 3D and now 4D reconstruction.
Got it, like a detailed GPS for light rays.
Kind of, yeah. They also add a timestamp map for the temporal conditioning, telling it when each view was captured.
Makes sense.
Then they cleverly concatenate all this info, the RGB pixel data, the plucker coordinates for pose, the time map into a richer 10-channel feature map for each input view.
Why 10 channels?
Well, RGB is 3, plucker is 6, time is 1, so 3 plus 6 plus 1 equals 10. This channel-wise concatenation lets them bake in the per-pixel pose and time conditioning without needing extra positional embeddings, which simplifies the architecture a bit.
Clever. And then it processes this like a vision transformer.
Pretty much. This feature map is divided into non-overlapping patches, flattened into vector embeddings, and projected into tokens, the language the transformer understands.
Okay, so patches become tokens. Then what?
Then these image tokens are fed through a series of standard transformer blocks.
And the transformer's job here
is basically to learn the really complex, intricate relationships between all these different input views and their temporal context.
Yeah.
It's figuring out how the object looks and moves and changes over time and across different viewpoints, just from these scattered inputs.
It's finding the patterns in space and time.
Exactly. And the output of these transformer blocks, the resulting tokens are then unpatchified, sort of put back together spatially, and decoded by a simple linear layer directly into pixel-aligned 4D Gaussian primitives.
Pixel-aligned, so one Gaussian per input pixel.
Roughly, yeah. For every input pixel, a 4D Gaussian is predicted. This direct regression is a key design choice. Makes it efficient.
That's neat. But what if the views are really sparse, like huge gaps?
Good question. They have an optional mechanism for that. The model can introduce additional learnable Gaussian tokens. They call these free Gaussians.
Free meaning?
Meaning they aren't tied to a specific input pixel. They're freeform and offer more generative flexibility, especially when you don't have much input data covering a certain area or time.
So they can kind of fill in the blanks generatively?
Sort of, yeah. Gives it more power when data is scarce.
Okay, and how is this whole thing trained? What's the goal?
During training, the goal is pretty straightforward. The model uses the 4D Gaussians it predicted to render images from specific viewpoints and times called supervision views.
Okay.
And it basically tries to minimize the difference between its rendered image and the actual ground truth image for that view time.
Making its picture look like the real picture.
Exactly. They use a loss function that's a mix of mean squared error MSE for pixel accuracy and also a perceptual loss, like LP-IPS, to make sure it looks good visually, not just pixel perfect, but blurry or weird.
Right, captures both fidelity and quality.
Precisely.
Okay, so that's the theory and the architecture. Sounds powerful. How did it actually perform in practice? Let's get into the experiments.
All right, the crucial part. So to train this at scale, they actually had to construct a specialized 4D data set.
Oh, interesting. From where?
Primarily derived from Objaverse, which is this huge repository of 3D objects. They curated about 32,000 animated objects from it.
Okay.
And then very cleverly, they augmented this with a massive number, 783,000 of static 3D objects.
Static. How does that help train a 4D model?
They treated each static object as if it were a short 24-frame video, but with only tiny, almost imperceptible displacements between frames.
Ah, so it still provided some temporal signal, even if minimal.
Exactly. It massively increased the data diversity for spatial structures without needing fully animated data for everything.
Smart way to boost the data set size. And how did they test it?
For evaluation, they used a standard benchmark called the Consistent 4D dataset and also a challenging holdout test set they made from their Objaverse 4D data. And they were careful about data leakage, making sure test objects weren't seen during training.
Good practice. And the training itself sounds computationally heavy.
It definitely requires significant resources. They used a smart curriculum learning strategy.
Meaning?
They first pre-trained the model at a lower resolution, 128 by 128, for about 100,000 steps. Then they continued training at a higher resolution, 256 by 256, for another 20,000 steps.
Why do it in stages like that?
It significantly reduces the computational cost compared to training at high res from the start. Even so, it used 160 A100 GPUs. So yeah, not small.
Wow, okay.
And for applications like 4D generation, they mentioned they fine-tuned it further, adding about 4096 of those free Gaussians we talked about.
Right, the generative ones. And they paired it with diffusion models then?
Yes, to showcase generating novel 4D content.
Okay, so how did they set up the actual tests? What inputs did they give it?
They were very systematic. They designed various input camera configurations to really push the model. Things like alternating canonical views, where the camera view cycles through standard directions like front, left, back, right across different frames, tests basic reconstruction. Then frame interpolation, specifically designed to test temporal interpolation. They intentionally omitted all the odd-numbered frames from the input.
So the model had to guess what happened in between.
Exactly. A tough test for temporal understanding. They also had 2 rotating cameras providing complementary views and random input views.
Random sounds hard.
Very. It introduces high variability with just a single randomly selected view for each frame. Really tests robustness to sparse and unpredictable input.
And who did they compare it against? The baselines.
They compared 4D-LRM against, first, a strong 3D baseline. GSLRM, which is like their model, but only does 3D Gaussian splatting. They ran it either per frame independently or try to optimize it jointly across frames.
Okay.
And also against shape of motion, or SAM, which is one of those optimization-based methods we discussed earlier.
Right, the ones needing dense data.
They also did ablation studies testing different model sizes. They had a large 300 million parameter one versus a base 85 million one, different resolutions, and different initialization strategies.
Like starting with weights from the 3D model?
Exactly. They wanted to see if that helped kickstart the 4D training. And they used standard image quality metrics, PSNR, SSIM, LPIPS.
Okay, the usual suspects for image comparison. So, drum roll. What were the main results? Did it work?
In short, yes, very well. 4D-LRM demonstrated really strong performance across all those different camera setups on both data sets they tested.
Even the tough ones?
Even the tough ones. It got PSNR scores over 30 in the less challenging setups, which is quite good.
Nice.
But, crucially, it proved robust even in those difficult settings with limited spatiotemporal coverage, like the missing frames test or the random inputs.
That's impressive. Did model size matter?
It did. They found, as you might expect, that increasing the model size generally improved performance, and that initialization strategy. Using weights from a pre-trained 3D GSLRM.
Did it help?
Yes, it further enhanced performance and sped up convergence, so leveraging prior 3D knowledge was beneficial.
Okay, and how did it stack up against those baselines, the 3D LRM and the optimization one?
This is key. 4D-LRM consistently outperformed the per-frame 3D reconstruction methods like GSLRM.
Why?
Because it effectively leverages the joint spatial and temporal information. It looks across time, not just frame by frame. The 3D GSLRM only performed comparably when it had really dense view coverage available.
Which, again, you don't always have.
Exactly. And compared to the optimization-based method, shape of motion. So TLRM really struggled in scenarios with those unconstrained, sparse inputs like the random views.
Right.
It just highlights the advantage of 4D-LRM's learned, generalizable representation over methods that optimize heavily per scene. The qualitative examples in the paper also really showed that 4D-LRM could generalize to new objects and interpolate smoothly over time, even with big gaps in the input frames.
Okay, so strong on reconstruction. What about the generation application?
Also successful. When they fine-tuned it with the free Gaussians and chained it with a diffusion model like SV3D, it actually outperformed existing generation-based methods on a standard benchmark.
Why do you think that is?
The paper argues it's because 4D-LRM produces more faithful reconstructions as its starting point. Even with the motion ambiguity inherent in generation, having a better underlying 4D structure helps the diffusion model produce better, more consistent results.
So a better foundation leads to better generation.
Seems so.
And efficiency. You mentioned 160 GPUs for training, but what about using it? Inference time.
The efficiency is actually quite remarkable for inference. The core 4D-LRM model takes less than 1.5 seconds for a forward pass on a 24-frame sequence using just a single A100 GPU.
Wow, that's fast for generating a whole dynamic sequence representation.
It is. They point out that the main computational bottleneck for the generation task actually lies in the diffusion model it's paired with, not in 4D-LRM itself. 4D-LRM provides the 4D structure quickly.
Okay, that's impressive performance. Now let's dig into the why. Why does it work so well, especially the frame interpolation part? That seems almost magical.
It is fascinating, right? The paper suggests its strong interpolation capability comes directly from its core design. Remember how time is modeled as a continuous distribution within the 4D Gaussians, not just discrete steps.
Right, the unified space-time thing.
Exactly. So when timestamps are missing in the input, 4D-LRM learns to intelligently reallocate some of its Gaussian resources towards these missing temporal regions. It actively tries to fill the gaps based on the motion it has seen.
It's not just ignoring the gaps, it's modeling them.
Precisely. It's understanding the underlying continuous motion. They observed that in these interpolation settings, the predicted 4D Gaussian primitives often have larger temporal variance. Their 8 value is bigger.
Meaning they smear across time more.
Kind of. They have a broader temporal influence, which helps bridge the gaps and improves interpolation quality. It's like the model learns to stretch its knowledge across the timeline where needed.
That makes intuitive sense. What else did they find in their analyses, training dynamics?
Yeah, they looked at training time scaling. They found, for instance, that increasing the number of target views, the views the model tries to predict during training, slightly speeds up convergence. Makes sense, more signal.
Okay.
Interestingly, introducing those free Gaussians from scratch, that actually slowed down the initial training convergence a bit.
Even though they help later for generation.
Right. There's a bit of a trade-off there initially, perhaps harder to optimize everything at once.
What about the space-time formulation itself? Was 4DGS definitely the way to go?
They compared it implicitly and found that their unified space-time formulation using 4DGS seems more expressive than alternatives they considered, like methods based on hex planes, which represent scenes differently.
Okay, and here's a finding I thought was really interesting. Enforcing strict temporal alignment actually hurt performance.
Yeah, isn't that counterintuitive? If they force the temporal center of each Gaussian to exactly match the input frame time it came from,
Performance got worse.
degraded, yes. This really reinforces the idea that 4D-LRM benefits from having the flexibility to redistribute its Gaussians, to let them shift slightly in time to better represent the continuous motion, especially filling those unseen intervals.
So letting the model figure out the precise timing is better than forcing it.
Seems so. It needs that flexibility.
What about scaling at inference time? Does giving it more input views always help?
Generally, yes, performance improves with more input views, but only up to a point. They found it sort of peaked around 48 input views.
And beyond that,
Performance could actually decline slightly.
why would more views hurt?
They suggest two potential reasons. One, maybe too many input views lead to predicting too many overlapping Gaussians, sort of overcrowding the 4D representation and reducing the final rendering quality.
Okay, too much of a good thing.
Possibly. And second, the transformer architecture itself might start to struggle with processing very, very long input sequences of tokens. There are limits to the context window.
Right, that points towards future work then.
Definitely. Future work on architectures that can handle much longer contexts, hundreds of views, perhaps, and maybe even things like test time training or adaptation to make it even more robust when you give it a lot of input.
Okay, stepping back a bit. How does 4D-LRM fit into the bigger picture, the related work?
It clearly builds on the success and efficiency of Gaussian splatting for 3D scenes. That's its foundation.
But extends it to the dynamic 4D domain.
Exactly. And that distinguishes it from, say, earlier dynamic scene work using things like neural radiance fields or NERFs. Dynamic NERFs can be very powerful, but are often much slower to train and render.
Right, NERFs optimize a continuous function, while Gaussians are more like discrete primitives.
You got it. And 4D-LRM represents a significant step forward in what are called feed-forward reconstruction models. Unlike optimization methods, it learns a direct mapping from input images to the 4D representation in a single pass, leveraging large-scale pre-training.
And it seems to be the first LRM specifically designed for this general 4D reconstruction task, handling sparse views, missing times.
As far as the paper claims and the field looks, yes. It seems to be the first large model tackling this specific challenging version of the 4D reconstruction problem in a feed-forward way.
Okay, so let's try to wrap this incredible deep dive up. What's the key takeaway contribution of 4D LRM?
I'd say the key contribution is being the first large-scale 4D reconstruction model that can really handle unconstrained views and timestamps.
Right.
To then let you render arbitrary novel view time combinations. You give it sparse input, gives you a full 4D output.
And it does this by learning that unified spatiotemporal representation,
Using those per-pixel predicted 4D Gaussian primitives.
which allows for fast, high-quality rendering, potentially at, as they say, an infinite frame rate conceptually, because time is continuous.
Exactly. And the scaling of the spatiotemporal pre-training is shown to significantly boost both the accuracy and the efficiency.
Okay, powerful stuff. But no model is perfect. What are the limitations? Where does this go next?
Right. Future directions are always interesting. One clear area is handling long context.
We touched on that.
Yeah. It can't yet efficiently process, say, hundreds of input images in one go. And its maximum training resolution was 256 by 256. While it generalizes okay to 512 by 512, fine-tuning at that scale is very costly.
So higher resolution, more inputs.
Exactly. Future work aims for high-res 4D reconstruction, maybe from hundreds of 1K or even 2K input images. That'll likely require new architectural ideas, maybe hybrid models.
What else?
Another exciting direction is removing the 3D inductive bias.
Meaning?
Well, right now, 4D LRM relies on having posed images knowing the camera position for each input frame. And it explicitly learns these 3D, 4D Gaussian primitives.
Okay.
Future work could aim to reconstruct directly from unposed images, maybe figuring out the camera poses in the scene simultaneously, or even design architectures that move away from explicit 3D representations altogether.
Wow, just feed it raw video from a phone, no tracking.
That would be the dream, right? A huge challenge, but a potential direction.
Absolutely. Anything else?
And the final big one is scaling from objects to scenes.
Right now it's mostly trained on single objects.
Primarily, yes. Scaling this up to reconstruct entire dynamic scenes like a busy street, or a room full of interacting people that's way more complex.
Why is that so much harder?
You have occlusions, things moving behind other things, complex interactions, much larger scale. You'd need new data sets, new training methods to handle the sheer complexity of large environments.
Yeah, like you said earlier, trying to build a digital twin of a whole city from just a few street corner photos.
It's that kind of jump in complexity. It'll require totally new ways of thinking about the data and the models.
Okay, so this tech is clearly still evolving, but the potential is just, well, mind-blowing.
Absolutely.
So for you, our listener, here's a final provocative thought to chew on. Imagine a future where you can provide just a few shaky, maybe random video clips from a live event, maybe a concert, a sports game, even just a family gathering, and instantly generate a perfectly smooth, photorealistic 4D reconstruction, one that lets you view the action from any angle you choose at any moment in time you pick. What kind of new experiences or maybe new forms of storytelling might that unlock, being able to truly relive and explore moments like that?
The possibilities feel pretty immense when you can reconstruct and interact with reality with that level of flexibility.
Absolutely. And that concludes our deep dive into 4D-LRM. Really fascinating paper.
Definitely cutting edge stuff.
Thanks for joining us. We'll see you next time on The Deep Dive.